Alright, this is our online video about scientific processes. This is something that you've been learning since elementary school and again in middle school. And in high school, we're going to further refine our definitions of what it means to do science. So here's a list of objectives. You'll receive these at the beginning of every online video. These are just the most key concepts that we want you to get out of the video. Many students that have been successful in the class said that they would go back and check this list of objectives at the end of a video to make sure they understood everything. And if they struggled with one of the points, then they would re-watch that section of the video. So just a little study tip for you there. So what does it mean when you say I'm in a science class? What are you doing? Science in its most basic definition is purely seeking the truth. And in biology, that truth is about the natural world around us, anything that is living, that is a part of nature. So it becomes this back and forth between asking questions and then finding out the answers to those questions. When we do science, we purposely try to reduce emotional reactions. In other words, what we want to do is we want to keep our science pursuits objective. And that sort of means without a bias or without an opinion. If the goal of science is to seek the truth, then the truth cannot be persuaded in any sort of way. So it's very important. And just a neat quote here, the scientist is motivated primarily by curiosity and a desire for truth. Again, reinforcing asking those questions and seeking the truth to whatever those questions are. So here you see we have an animation of a student who is doing science. He has put together an experiment where he mixes together two liquids, and then from that he gets a crazy reaction. And as you can see, he's very excited by that. But that might lead you to say, well, why? What are the properties of these two liquids? What caused the change in volume and things like that? You can also ask other questions, like for example, on the other side here, this is a picture of a very famous behavior scientist. And basically what has happened here is he has learned that at a very, very young age, these little goslings are going to follow whoever they think is their mother. They're going to imprint on their mother. And in this case, it happened to be the scientist who was doing the experiment. So, you ask your questions, design experiments, and then you go get your answers for them. Okay, so as you have learned about the scientific method, that's exactly what it's been called, a method. And what that implies is that there is one way to conduct science and only one way. It is a series of steps. You must follow them in this exact order. You must move all the way through all of these steps, and then, you're finished. You've done science. But in reality, we need to be a little bit more flexible. One thing that is at the center of all scientific processes are questions. So you can observe and that leads you to a question. Or you could experiment and gather data and then that leads you to a different question. Or when you reflect on your findings, further questions have developed. So as you can see, going around the outside of this diagram here are lots of different parts that were originally the scientific method, but now they're not linear, okay? They can happen in any sort of manner. So, a scientist could pose a question, like form a study question, let's say, and then it bounces them back to another question, which has them redefine their problem and reform a different study question. So you can sort of bounce all around in this sense. We just want you to get comfortable with seeing some of these terms as things that you do when you are conducting science. So, we're doing science. We're going to do lots of science in this class. There are two basic branches to ways that science can happen. Okay? And the first is what we call discovery-based. So here we're focused on inquiry, which is the idea that we're doing a lot of observing and then asking questions about those observations and continuing to make further observations. It's not very structured, and so a good example of this would be Jane Goodall, and she is very well known for her work with chimpanzees. When she decided to study chimpanzees, she didn't go in there with an experiment already designed that she was going to conduct. She merely observed, and based on her observations, she started putting together questions. Like, for example, when these two males meet, they exchange a certain behavior, and it looks like a form of communication. I wonder if that's the same as between a male and female. So questions like that would be discovery based. In our class, we are mostly going to be focusing on hypothesis based science. So that means before we even conduct any science, we're going to draw up a question and then we're going to design an experiment around that question. So you can see here this was some sort of a plant growth experiment. They have specifically set up an environment that is lighted for the plants to grow in. They've labeled all the pots. It looks like they have different treatment levels and things like that. So they have one question and they have designed an experiment in order to answer it. So, in order to describe scientific process and the basics of hypothesis-based science specifically, we're going to walk ourselves through this model. So, we are going to start with a question, and this is a question you may have asked yourself. Do flea collars on dogs really work? This question came from just everyday life. It did not require a degree. It did not happen in a lab. Simply while walking my dog one day when I was in high school, noticing other dogs with flea collars, you really start thinking, wow, I wonder if they work. These companies all here, they make billions of dollars a year selling their products, but the question is, should we believe them just because they say, oh, they will kill fleas and ticks for 7 months, and they'll have 99% of repelling and things like that. Instead of just accepting something like that, where they just say it on the box, as a scientist, we want to test that. So we have a question, and now we're going to seek out the answer for it. So we're going to design an experiment to determine if flea collars really work. So we need to start identifying our variables. And again, you should be familiar with these terms, so this is more of a review. Your independent variable is the part of the experiment that you are purposefully changing or manipulating. So this is what we are testing. Then the dependent variable is the measurable outcome of the experiment. So it's what changes in response to the independent variable. So when you think dependent, think D for data. So independent is what we're purposefully changing about the experiment. Dependent is what we're measuring as the outcome of the experiment. When you collect the data from the experiment, you have lots of different options. So your dependent variable, you could have one, you could have several. So what type of information do we want to collect from an experiment? Well, in this one, we could collect qualitative data or quantitative data. And when you look at the word qualitative, you should see the word quality in there. These are results and data that we can't measure numerically, but may still be valuable. For example, we could measure how the dogs demonstrated itching behavior. Is that something you can put a number to? No, not really. The other thing is it tends to be much more subjective, which means it's open to opinion. So if I am observing dogs and let's say that I am recording my data, and for dog number 23, I feel as though they showed itching behavior 7 times. If someone else came and observed the same dog at the same time, they might have thought that they itched, like 9 times. So it's not very reliable. In biology and in the other hard sciences as well, like chemistry and physics, we like to rely on quantitative data. Okay, so our focus is going to be on our quantitative data. Again, it is very objective. It's based on numerical results. For example, at the end of this experiment, maybe we count how many fleas are on each dog. Well, when you count something, you should be able to get the same count as another person. There's no opinion as to, how many fleas were here. You have physically counted, and so you can compare that. So we're going to always try and focus on using quantitative data. So our variables for this experiment, our IV, our independent variable, will be the wearing of a flea collar. That's what we're purposefully making different in this experiment. This is what we're testing. And how are we going to measure that? Let's use a quantitative data collection and let's count the number of fleas that are found on a dog. So now we have the basics. Okay, we need to refine a few other variables. So we have a group that's going to have flea collars, and we have a group that's not going to have flea collars, and then we're going to count the number of fleas on them at the end of our experiment. Now we need to identify our constants, or another term for that would be controlled variables. These are aspects of an experiment that need to be the same between all test groups. So the idea is you want to test one independent variable at a time. So all we're looking at to make different between these groups is the fact that this group has a dog collar on and this group does not. So let's try and think about some of the things that we want to keep constant between the groups. And on the bottom here I have a few pictures just to sort of get your mind thinking. Pause the video here and see if you can make a list on the next slide and then fill in whatever I add in that you didn't think of. Okay, so let's take a look at what you came up with. Some ideas here, things that must remain the same between both groups. The same diet, okay? We need to feed them the same amount, the same brand, and the same type of food at the same time of each day. How about exercise? We want to make sure, again, that they're getting the same amount and type of exercise at the same type of day. Hygiene, how often they are being brushed or washed. Their environment, are they living in like the same kind of geographic location, same temperature, etc., things like that. And housing, are they sleeping outside in a, are they being kept in a kennel inside, things like that. So the bottom line here is, in your experiment, you want to control for as many of these variables as you can, these CVs. Because that way, when you get the results of your experiment, you have confidence that the only reason you got differences in your two groups is because one group had the flea collar and the other did not. So, for example, imagine if what's the example I always use? Oh, imagine if I wanted to find out why my pencil sharpener was broken. Okay, it happens in school all the time. And I want to find out the one reason why. But I open up the pencil sharpener, and in addition to cleaning out the shavings case, I also tighten some of the screws and I wash out the inside. When I put my pencil sharpener back together, it works just fine. So now what's the reason why? Was it because of the pencil shavings? Was it because I tightened the screws? We don't know because I overlapped those variables all at the same time. So you want to make sure you have one independent variable and that you keep all other variables constant. That is a key part of designing a controlled experiment. So we talked briefly about this. Your test groups are going to fall into two categories. Your experimental groups are going to be the ones that receive whatever your independent variable is. And your control group will be one that does not get the independent variable. And so the idea is you want to compare the two of them, the haves and the have-nots. That's the basic idea behind the experimental and the control. So in our design here, we have our control group, okay? We have a group of dogs, and we have our experimental group. Same makeup of the same group of dogs, except you can see that they all have a flea collar on them. So the idea is we want to keep them in identical conditions, time them for the same amount of time. I suggested 2 weeks. And then at the end, we're going to count the fleas on each dog. So hooray, you have designed an experiment. Okay, before you perform the experiment, you want to put together a hypothesis. And a hypothesis, the best way to describe it is that it's like a prediction. Okay? In your middle school classes, I know that they use a lot of the terms of an educated guess. We want to make this much more formal at this point. We don't want to use the word I think, okay? Because we know that with that phrase, of course, a hypothesis is going to be what you think. So now we're going to turn it into a statement. It is an if-then statement. So it takes on a specific format. Within your hypothesis, you also want to be able to identify your IV and your DV. And you want to make sure that your hypothesis is something that's testable. Because at the end of your experiment, you're going to come back and see, did I support my hypothesis or do I have to reject my hypothesis? So if it's not testable, then the hypothesis is worthless. A good example, something that we can't test in science, a question like, does God exist? Okay, to turn that into a hypothesis, there's no point because there's no way that we can provide proof, any sort of scientific evidence to support the hypothesis. So here is a hypothesis that I have worded. I like the wording of this, wink, wink, nudge, nudge. Make sure that you word your hypotheses like this for all lab experiments. So we have if dogs are given flea collars, and here we've identified the IV, then the dogs that are wearing the collars will have fewer fleas compared to dogs without collars, and the number of fleas is identifying my dependent variable. That is a very complete and properly formatted hypothesis. When you form a hypothesis, sometimes you might hear it called a claim, okay? Because when you perform your experiment and you put together your hypothesis, in a sense you're trying to argue the outcome of your experiment. And so you're going to make this claim with your hypothesis. You're going to say, yes, dogs that wear flea collars will have fewer fleas, or you're going to say, no, dogs that wear flea collars will not have fewer fleas. They show no difference. So we're going to see some wording like this as we go through, and keep these things in mind for when you write up summaries. So now you've done your experiment, okay? And from that experiment, you have collected a lot of data or information that you got while performing the experiment. So an example of data would be simply the counts. Okay, maybe you average them together. So in the control group, the average was 12 fleas per dog, whereas in the experimental group, the average was 3 fleas per dog. And let's just say that was your outcome. All of that is just data, okay? At this point, we would call this, this is your evidence. This is information you received from your experiment, and you're then going to use this information to either support or reject your hypothesis, your claim. So if that's data, then what does it mean to go through an analysis of data? So when you look at the numbers, okay, a lot of students, when they're writing a summary, they would stop here. But you need to explain the why behind your data. And so what meaning do those numbers have? Why are there differences between the groups? One 12 fleas and the other one 3 fleas. So you need to start to provide some reasoning for the evidence that you obtained. Okay? It doesn't help your claim to just say, well, these are the results and that is that. You have to back it up and explain why the results you got makes sense, what meaning it has. So here's an example. Okay, why do you think there would be a difference? Well, perhaps there is some sort of a chemical in the collar that makes it unpleasant for fleas. So when a flea lands on that dog, they're less likely to stay and make a home there. That's providing an explanation for why you received a difference in your data between the two groups. So we've got claim, then you have the evidence obtained from your experiment, and then you provide the reasoning for why the evidence supports or rejects your claim. So keep those words in mind. We're going to be talking about a lot of that as we go through informal lab report writing. The last thing you want to do when you finish an experiment is to wrap things up and, most importantly, communicate your findings. So after you have done an analysis and explained why your data came out the way it did, you provided the reasoning for the evidence you collected, you either accept or reject your hypothesis. Question: if you reject your hypothesis, does that mean you are a failure as a scientist and you should just give up and pack it in? No, not even close. A hypothesis is simply a prediction. And remember, science is all about seeking the truth. Whether you guessed right or not, you need to just communicate what the truth was, okay? If our data turned out differently, then we would have to reject our hypothesis and say there was no significant difference between the two groups. Therefore, the flea collars do not appear to have any effect on the number of fleas on each dog. When you identify sources of error, this is a really big part of summing up a lab, and it's something a lot of students always forget when they are doing things. Sources of error. The best way to sum this up is when you are doing science and you are working for a company, they're giving you a lot of their money, and they are trusting you to find these answers for them and report back to them. So mistakes can happen, okay? We're all human, that's understandable. But you want to make sure that your science is as clean as possible, that you made your measurements exactly perfect, that you controlled all other variables, that your equipment was top-notch. But just in case it wasn't and you didn't know about it, you create a list of sources of error. So if someone down the road comes back and does your experiment again, just as you did, but they get different results, these might be some of the things that could have happened unknown to you. That's key right here. Unknown to the scientist. So let's say, for example, you were doing some sort of chemistry experiment and you thought that you made a 20% concentration, but really it was more like 23%, and that may have thrown off your data a little bit. You don't know that happened, okay? You assume you measured it properly and it was 20%, but by accident you made the wrong percentage, and that's something that you have to account for. Most often it's going to be a human error. As I said, we are making mistakes all the time. Okay, and you just want to account for that. You want to say, hey, listen, I'm human. I did this experiment the best that I could, as cleanly and as accurately as possible. But if I made a mistake, here are a list of places where I could have made a mistake. And then most importantly, you need to communicate your results. Why is it important to society? Or why is it important to the scientific community? You would think a flea collar experiment doesn't sound very important, but a billion-dollar industry has been built on this science that flea collars work. So it is important for you to ask those questions and then seek those answers through scientific experimentation. And hopefully this online video lecture is giving you some tools so that when you walk into the classroom this week, we will be able to perform our first experimental design together. Alright, this is the end of our online video. If you have any questions, remember you can always email your teacher. I suggest at this point that you go back, check your objectives, make sure you can answer them thoroughly, and if not, go ahead and watch the OV again.